Hey everybody, and welcome to another episode of Space Science with Python. Now, before we dive into the project that we are going to conduct in the next couple of weeks and months, I would like to personalize my videos now a little bit by showing myself in the beginning to engage a little bit more with the community here on YouTube, on Reddit, Twitter, or Mastodon. So yeah, you see now myself and my surroundings. And you also notice that my setup is not really professional, right? I should improve the video quality, the audio quality, and also the light setup. So if you have any suggestions or good ideas how to improve it, if you know a good camera or so, just write something in the comments so I can professionalize myself and this channel here in the next couple of weeks and months. But I think since this is still a small niche channel and yeah, it's not a channel with thousands or hundreds of thousands of subscribers, I think that's a good starting point, so to speak. Now, today we are starting with data from a spacecraft called Cassini. So some of you have heard about the NASA Cassini spacecraft and NASA Huygens, sometimes also called a spacecraft, as you see here in this image. An image that is more a render or an artistic impression of the Cassini spacecraft, and in the background you see, for example, also Saturn and some instruments on the Cassini spacecraft, and also the propulsion that is in this photo being activated. Now, small data about it. Well, it was started in 1997 and reached Saturn after 7 years of interplanetary cruise time. And directly in the beginning, it also deployed the Huygens probe, you see here, that then landed on the surface of the moon Titan. So I can see here a quick paste up video of the Titan recordings during the landing phase. Now, the question is now, okay, what kind of data can we use to conduct maybe some kind of scientific project here in our YouTube video series? Well, I would like to put this at the very end. So as some of you have followed my videos already, you know that I'm into meteors and asteroids, near-Earth objects and cosmic dust. So it will be related probably something with small particles in the Saturnian system. But before we go into the scientific objective we are conducting in the next couple of weeks and months, I would suggest that we are going into a small presentation just to give you an overview of the Cassini mission. And of course, this short video cannot even remotely summarize the entire scientific output of the Cassini-Huygens mission. So I was part of one of the instrument team, and I have to say, of course, I'm very biased, and Cassini is one of the most remarkable missions, I think, in human space exploration. So it is very difficult to make a video maybe for only 20-30 minutes to really summarize all the amazing scientific outputs that have been generated. I would suggest to put these scientific insights into another video, and we'll just go into the hard facts of Cassini, and then we will take a look what instrument we will focus on, how the instrument works, and what the next videos will be all about. Now, one thing in between. I think I will not put the entire topic into one YouTube series and just create videos all over the time with this topic, but it will be separated in sub-projects or subtopics, so that we will do like 3-4 videos or tutorials about a Cassini topic, then we will jump over to some, let's say, generic or general topic videos about maybe astronomy and also other things, so that we keep a very diverse and we cover a lot of different topics. And then we jump to another sub project where we are then working on another subtopic of our scientific goals. So I think this project will be pretty huge. It will take us, I don't know, maybe like 8 or 9 months. So I would like to really put it into pieces. So if somebody of you doesn't really like the topic or doesn't like to work with these kind of data, don't worry. I will just put it into small chunks and upload also other topics in between. But I would suggest let's jump into the presentation I prepared, and it's just a few slides where I would like to show you what Cassini is all about. Now, I think instead of really describing all the instruments, I would suggest to take this poster NASA created at the very end of the Cassini mission that pretty nicely summarizes the mission in numbers, or as they say, Cassini, Huygens mission to Saturn by the numbers. So just a few random numbers, really difficult to comprehend. For example, the first one, 2.5 million commands have been executed. 4.9 billion miles have been traveled, respectively, around 8 billion kilometers. But the data that come up now are maybe more relatable for us as a data science community. So we have in total 640 gigabytes of science data collected, and we are not talking like data in a format that it's easy interpretable, like you know it maybe from other data science projects. No, we are talking really about binary data that have to be unzipped or unpacked to really work on. We will take a look at this also later when we are working with our instrument data. In total, around 4,000 science papers have been published, and it shows the immense data lake that has been created, and also the scientific derived insights. It's pretty amazing. And as I said, one cannot really comprehend these numbers, right? I mean, I wrote my PhD thesis on one particular instrument with particular data, and it's like only a very tiny fraction of the entire scientific community that was or is around the Cassini-Huygens spacecraft. In total, the Cassini probe completed almost 300 orbits around Saturn. So the orbit changed all the time. They used the propulsion system to make smaller or closer flybys to the moons, or to change the orbit in a way that they could conduct also different scientific objectives. And we will also use Python to visualize these orbits, and also some 3D rendering. So we will not really work all the time with science data, but also sometimes with the Cassini spacecraft itself to really get a feeling and understanding of the Saturnian system. Speaking of the Saturnian system, 6 new moons have been discovered. Well, the Saturn system has dozens of moons, so pretty large ones like Titan or Enceladus, but also smaller ones that are, I would say, almost asteroid-like. Now, also talking about the flybys, 160 flybys have been done. So this is pretty large, and a lot of flybys were at Titan. So they used Titan also frequently to alter the orbit of Cassini, or also stabilize the orbit. So it was more like a necessity to fly by at Titan to keep the orbit stable. Talking of images, but the instrument took almost 500,000 images, and you can go to the NASA website, you can download these images, you can work with them from a scientific perspective, or if you like, just download them to get a feeling and understanding how the Saturnian system looks like. I think these are pretty lot of images to get a good understanding. An international project. I said it's a NASA project, but in total there were 27 nations involved. The Cassini spacecraft itself is from NASA, but you see here the Huygens landing probe was a part from the European Space Agency. And at the very end here now, the number of 360 engine burns, the engine burns that were needed to alter the orbit, or to stabilize also the trajectory of the Cassini spacecraft. Now here a small scientific drawing of Cassini back from 1998. I think you get an understanding that we have a lot of instruments and so on. And if you're wondering, how one can really work on all these instruments, well, all instruments had their own team, right? So I was part here of this small instrument you see here, the cosmic dust analyzer, and this is also the instrument we will focus on in the next couple of weeks and months. Now, the cosmic dust analyzer itself had a, I would say, straightforward scientific objective. Its purpose was to, measure particles, cosmic dust particles. And you see, for example, here, the moon Enceladus, and here it's a little bit brighter, so you'll see some cryovolcanic activities, and all these dust particles that were created by Enceladus created or formed the so-called E-ring that you see here. So pretty large and diffuse. It also goes here to the outer parts. You can see Saturn is here on the right hand side, and the cosmic dust analyzer was able to detect tons and tons of these particles and make also measurements about their chemical composition. But we will talk about this just in a moment. Yeah, so here you see the Enceladus surface, for example, in a closer approach or flyby. Here you see the cryovolcanic activities, and Cassini was also flying through these volcanoes, and the instrument, the cosmic dust analyzer, or short CDA, was able to detect particles here and made some mass spectrometers. So it was determining the composition of the particles, so that the team of CDA was able to, for example, determine that below the ice surface of Enceladus there has to be a liquid ocean. And I think this is a paper published in Nature or Science several years ago. Now the cosmic dust analyzer here marked, you see it points into one certain direction, but this is just on half the truth. The instrument itself was able to, as we called, articulate, or you can say rotate at a certain angle over 250 degrees to really adapt to maybe more beneficial geometric configurations to be able to detect way more dust particles. Of course, the instrument itself rotated into certain directions so that the camera was pointing sometimes, or other instruments had their, as you call it, prime time to really focus on scientific objectives. And because CDA was also sometimes part of this prime time, but in the meantime we were able to use the articulation or the rotation axis to improve the geometric properties of CDA to detect more particles. Now CDA itself looked like this. You see here it consists of two parts. Here you see the articulation table, and we have here the dust analyzer that was able to detect the spectrum, so the mass spectrum of the particles. And here you see the so-called high rate detector, but we will ignore this part of the instrument. We will focus exclusively on the larger part. And just a few numbers, well, it was around 16 kilos and 11 watts of power. You see here, just to get you an understanding and feeling about the data we speak, 0.5 kilobits per second was the peak data rate of the instrument, and the dimensions. So you see here around 0.5 meter of length and almost 0.5 meter diameter here, so that if a particle was flying here, we were able to detect different properties. I will just tell you in a moment, and also the chemical composition. Now this is the cross-section of the instrument. Looks very difficult, but I would suggest to go quickly through it, and I think with a little bit guidance. So you see here two possible events of a dust particle entrance. On the right side is like the blue trajectory. The dust particle was flying through the instrument through these grids. You see the grids here on the right hand side with the mounting. And first it was going through a channel called the QP channel, so the entrance grid. And well, every particle in space is charged, right? So you have a particle, some radiation is hitting the particle, electrons are flying away, so the particle is positively charged, and this charge can be measured, for example, here in this entrance grid. So you see here some signals. It flies and flies and flies, and it hits at some point this so-called chemical analyzer target CAT. And CAT was coated with rhodium, and when the particle hit the surface, you saw more signals. Here you have, for example, the QC channel, for example, then the signal looked maybe like this or so. And the impact velocity is not like a few centimeters or inches per second or per hour. These were really a few kilometers per second, so several miles per second impact speed. And this means that a small particle of only a few micrometers size really vaporized, right? It was just destroyed into its atomic fractions and into its chemical compositions, into a lot of ions. And these ions were then gathering here. They were then accelerated. You see here a voltage of +1 kilovolt and here -350 volt. And this means that the lighter particles, like for example protons or also charged helium particles, were flying into this direction quicker than heavier elements, like for example potassium or iron, so that a lot of different particles were hitting this so-called multiplier at different times. And this is what is called the time of flight spectrometer. Yeah, lighter particles reach the instrument first, heavier are coming later on. And there you see here MP, the channel, like this, I don't know how to describe it, like a comb structure, where you see, for example, here maybe helium and then potassium, iron, and at the very end, rhodium, which was part of the coating. So this was then being used also for calibration to really get an understanding, okay, how does the spectrum look like? The other channel here was the ion collector QI. This will also be important in the future. So you see here the signal. We will not get into detail about these individual signals, but this is how the instrument basically worked. We had also another impact. This was the impact ionization detector IID with the channel QT. And these ions were also accelerated to the multiplier. But since there was not a voltage of 1 kilovolt, let's say this cloud of ions was reaching the multiplier as a diffuse cloud. So you were not really able to get a spectrum, but at least you got some information on this so-called QI channel that allows you to determine the velocity and the mass of the particles. The third event, of course, is an impact on the wall. So the particle flies like this and hits the wall, but these are just edge cases we are not considering in our work at all. Now, what is the purpose of this project series? What are we going to do in the next couple of weeks and months? So I was asking the question, okay, what kind of data product do we want to create? And my suggestion is that we are creating a database with astrodynamical properties of all measured dust particles. So just to give you a number, we measured not 100 or 1,000 particles, but 100,000s of particles. Of course, also with noise events and so on, but we have a lot of particles in there. And since we have like here the pointing of the instruments and so on, of course, with a certain uncertainty, we could determine the velocity, the mass, and so on, and then really see where these particles came from, what were their orbits, and so on. So this would be, I think, a pretty nice, interesting task. But first, we need to calibrate our instrument. Calibration has been done in the past on Earth in laboratory experiments, and we will do this in this very first part of our video, where we will use the data from the calibration work, and we will use machine learning to calibrate instrument data. I think this is really pretty interesting, and for anybody who's working on also on instruments, either in the laboratory or maybe also in industry, calibration of instruments with machine learning is a pretty nice regression task. Afterwards, we will take also a look at the trajectory and pointing of Cassini. The pointing of the instruments, of course, is important. And then I would say creating a method to, well, compute the dynamics of the particles. But this is something for another future video, of course. So you see these different points, we will separate them in sub-projects so that you will not be bothered with one huge series, so that you have sometimes also different content to enjoy. Yeah, so again, this is the instrument. And afterwards we can conduct some astrodynamical science, but that's not the only thing. We will also use the spectra data to analyze these spectra. Yeah, so we will use machine learning. And just a small spoiler, I already did that, or I'm still doing it in the meantime as a guest scientist at the University of Berlin. But this is something maybe after this astrodynamical science topics I would suggest. Yeah, so that's basically it. This is what we are going to do in the next couple of weeks and months. And it is a huge task, I have to say. So some parts I will show you are also parts of my PhD thesis. So I try to condense everything I did in this 3-4 year PhD journey to put everything in these YouTube videos, in these Jupyter notebooks, and to give you an understanding how we can use space data to derive data scientific conclusions. For example, particles from outer space, particles from Enceladus, and so on. So it will be really difficult. I try to do my best to give you a good understanding and feeling how this looks like. We will do some science presentations, we will do some talks and discussions. If you have questions, put them into the comments, or just write me a mail, approach me on other social media channels. I think this is a pretty interesting topic we will do, but don't worry, we will separate this in several small sub-project chunks. So if you are bored at some point after, let's say, a few videos of Cassini and say, I would like to work on something else, don't worry, we will do it, because I would also like to update you with the most recent science work in astronomy and science. So that's the very start of our new Cassini project. The next video will be published next week, where we will start looking at the instrument calibration. So how has this been done? What kind of data do we have? And then there will be one, two more videos where we will use the existing calibration functions, and then we will use a machine learning approach, or a simple regression model, to see whether we can beat, in a way, the existing calibration functions that are there now since 20 years or so. So yeah, I hope you enjoyed this small introduction. I hope you are also looking forward into the topic of Cassini, and yeah, I hope you will enjoy the same enthusiasm as I have it. So thanks for watching, and see you next time.